So, my name is Max McNeil, and I really hate traffic. So picture this, right? You're running late to an important meeting, and you need to take the public transit. So you hop on the E-train, check the schedule, you know that the bus you're about to, or the train that you're about to take has been running 15 minutes late all week at the same time every single day. And so you miss your meeting, and your day is thrown completely off track, and you just feel horrible, right? So an analysis of the NYS Open Data Portal shows that transit delays vary by 25 to 45% throughout the day, making static schedules increasingly unreliable. And according to transportation studies, transit unpredictably costs New York commuters approximately $45 million, or 45 million hours of lost productivity. And so I came up with Transit Pulse, which is a real-time, AI-powered geospatial web platform that helps visualize, predict, and explain public transit delays across New York State. And through my solution, commuters can access accurate predictions, understand the context behind delays, and make informed decisions about their travel plans according to those delays. And so I implemented Transit Pulse as a monorepo using Turbo Repo and PnPM Workspace. And for the front end, I had a Next.js application using app router architecture, Shed C and UI components, Tailwind CSS, and Leaflet.js for the map. For my state management, I handled that through React Context API, combined with SWR for data fetching, built-in cache, and revalidation. On the back end, I have an Express server written in TypeScript, providing static type checking and improved code maintainability. And for data persistence, I integrated PostgreSQL with TypeORM for object-related mapping for my database. My API follows RESTful design and has an intelligent caching layer that stores the GTFS data for 24 hours, performance metrics for 6 hours, and real-time data for 5 minutes to optimize response times while maintaining data freshness. And I have an ML service that was built with Python and Fast API, which is async request handling and OpenAI documentation. And so I kind of was able to feed that directly into my IDE, which I chose Cursor, which is, I don't know if you guys know about Cursor. It's an AI-powered IDE, pretty fast development, kind of what let me get this done in like 3 hours. I was able to feed it that OpenAI API documentation because I was using Fast API, which is pretty sweet. I leveraged PyTorch for implementing my LSTM neural network for time series forecasting. The data processing pipelines were constructed using Pandas and NumPy for efficient numerical operations. And then for my natural language generation, I'm using Google's Gemini API for the custom prompt engineering. DevOps, I don't know if you care about this, but I containerized all the services using Docker and multi-stage builds. This is Turbo Repo for model repo management. I have GitHub Actions, etc. Kind of all these things came together to kind of help me get this done in a few hours. The intelligence layer of Transit Pulse, it uses two technologies. The first one being the LSTM-based delay prediction model, which processes historical transit delay patterns, considers the time of day, week, and route specifics, and then provides forecasts of the expected delays with confidence scores. The model uses a series of LSTM layers for dropout for with dropout for regularization, followed by dense layers for final prediction output. Second, to make technical data possible, I integrated Google's Gemini API to generate human-readable interpretations of that transit data. So my interactive map, which just recently broke, because like I mentioned, I was using Cursor, and so, you know, AI is like great, and then you tell it to do the wrong thing like one time, and it just screws up all your own code. So that is just like, you gotta just do it yourself. I mean, anyways, the interactive map, when it was working 5 minutes ago, visualizes real-time transit routes and statuses predicted by delay hotspots and environmental factors for affecting transit. So the analytics dashboard also prevents this historical performance trends, peak delay times, and route comparison tools. And it also uniquely provides natural language summaries using Gemini's API to describe delay patterns in plain English explanations and contextual reminders for commuters. The this solution kind of just empowers people to not only know that something is delayed, but kind of why it's delayed and what could be causing that delay, so you can kind of yourself predict that into the future, which I think would be pretty awesome. I'm a freshman now, going to RPI. Previously, I was living out in Brooklyn, and it was a constant issue. Just trying to get to class on time, but the delays running. Anyways.
Demo?
I'll do a demonstration now. There you go.
All right, questions?
My demonstration too.
Oh, lot, go. You're up and your time is up, so let's.
Okay, sorry. So here's the map when it was working. It shows the transits routes. So it also had a leaflet map, which displayed the traffic routes, delays, predictions, etc. The dashboard, after it loads, it's building. Yeah, okay. So we have the total routes, average delay between those routes, and the number of times it was on time, and then the active delays. And then additionally, it has the AI insights on the side too, which is like routes A and G underperform with delays 20% higher than system average. And recent precipitation resulted in a 15% increase across delays across all the routes in the north. Consider adding additional trains during 5 to 7 p.m. peak and monitor weather patterns, whatever. More route analysis. That's
All right.
not going to build. Yep. And then,
Judges, start asking questions. Yes, Josh.
So any plans to push this up, to scale this up to a Kubernetes cluster? You mentioned Docker.
not really. I don't think it's necessary for a project of this scale, to be honest. Yeah.
Questions? Yes.
So why you use so many technologies? I mean, why you do so much things?
I mean, you want to use all the things you got, you know. You want to stay on the frontier of development, and so I'm not really looking to work with old technologies and to work with all the newest ones.
Understanding those things are important or solving the problem?
Well, yeah, I mean, I'm a computer scientist, so if I'm not staying at the forefront of those technologies and employing as many of the new technologies that are coming out day by day, and then I'm behind on my work, I believe.
Aren't we all? Next question. All right, that's it.
So, thank you guys so much. I appreciate it.
Thank you. We have Endocrine Watch up, and we have public transit planning on deck. Public transit planning, where are you?
This is Dave. This is Mark. My name is Connor. I'm an expert in reproductive genetics and with a specialty in andrology. And that's one of the reasons why the idea that I worked on with these two was Endocrine Watch, an app that tracks endocrine disruptor exposure. Now, endocrine disruptors are chemicals that mainly harm the body's reproductive system, or also called reprotoxins. They constitute a serious harm recognized by the scientific community. It is a emerging field with serious implications for the ability for humans to continue the ability to reproduce. Honestly, they're everywhere in soaps, food, furniture, clothing, shampoo, cosmetic products, and plastics. If it's part of the modern day, it probably has some form of endocrine disruptor. That's not to say that all of them are extremely bad, just they're pretty much everywhere in at least some. Okay, many products contain endocrine disruptors, but it's difficult to find information about which products, and that's where this comes in. Endocrine Watch, an app that acts as a central hub for individuals to track their exposure to various endocrine disruptors. Our current main feature that would be like the founding base feature is they would input a product name and the app would list any endocrine disruptors contained in the product. The architecture would be a mobile app created with the .NET MAUI mobile framework. It's a very versatile framework that allows you to work on both Apple and Android in one project using the .NET framework. The user inputs the product name. The app checks an open data source which lists products and the ingredients they contain. The data source is a website with a specific HTML layout. The app executes a program to scrape the site for data info. And the app checks the ingredients list against an open data source containing a list of various endocrine disruptors, and you report the results to the user. Here is, we weren't able to finish a functional prototype, but I do have some screenshots from the code. So this would be, this is the class for deserializing the JSON data. This is actually deserializing the JSON data, and then it would have all the entries of the endocrine disruptors in one list. And then I just put down here, then a console.readline, so input, then a web request to get the product ingredient HTML. You would isolate the ingredient strings from HTML, make them a list, cross-check the list of ingredients with the list of disruptors, and then output. Now, future features to include. These would be the features that we would add on after the base. AI analysis of the impact of specific disruptors ranked on severity based on scientific studies. So, as I said before, endocrine disruptors are of varying severity. Some can cause extreme effects, including in pregnant women, male babies being born with genital defects, which is incredibly serious. Another thing is a map of where most of the impacts occur globally. This is the geospatial part. And also, the second geospatial part is the map showing the locations of stores that carry the most safe and low-risk products. Another thing, track personalized endocrine disruptor history, or disruptor exposure levels and history. This is important because this is an accumulatory type of toxin where it doesn't just like go into your body and then leave. Like some of them literally are lifelong accumulatory. An AI-assisted analysis of lifestyle risk factors based on open data sources such as government and regulatory agencies. An analysis of overall exposure impact by an AI trained on a vast set of open data based on endocrine disruptor science. And AI tailored recommendations for how to alter lifestyle for better endocrine health. And that is it.
Thank you.
Great. Everybody's doing their job. Questions? Yes.
So you've mentioned open data, open databases, but not any that actually exist. Do you have a plan for generating the open databases, or how would you go about attacking that part of the problem?
Well, the open databases that we would use would be things like the FDA API, IND, I can't remember the name of it right now. INDCI, I think. There's the Endocrine Disruptor Foundation. There's the European regulatory agency, which has open data on their banned endocrine disruptors. So there are multiple like data sets open data sets that we would be able to pull from.
Next question? Any? All right. Woo! We are moving on to number 7, public transit planning. Come on down, guys. Yeah.
All right. Hi guys. This is Public Transit Planner app. So plan, propose, and deploy. So let me here introduce the table of contents. We have the first slide is our team, so all of us. The problem, our solution, the timeline, a demo, and then some questions at the end. All right, meet the team. Hi, I'm William, Chartmeister.
I'm the old man. I'm the chief prompt engineer.
Crabapple. Amazing. All right.
All right, the problem. So we focus on public transit. Public transit is an important part to a multi-pronged issue. So one is environmental impact. So 30% of CO2 emissions come from the transportation industry, including cars, trucks, buses, etc. Severe traffic congestion contributes to that carbon footprint. So not only is it the traffic itself, but the congestion or the delay times in the traffic. Public safety, so crashes are the #1 cause of death for people under 18. There's 45,000 annual fatalities a year in the US, and that this metric is actually increasing year over year, or safety is declining year over year, so it's a problem that's exceeding. And social inequality, 20 to 30% of people don't drive in the capital region, so it's a pretty significant chunk of the population, probably a lot of students as well. So yeah, many issues that public transit can address.
I'd also like to mention, my brother got his driver's license today, so I just want to get everyone else if possible. Yeah, so with that in mind, to try and mitigate that problem, we use the metric of AADT, which is average annual daily traffic, to analyze which roads were most heavily used. And we use TED, which is total excessive delay, to find where congestion happens. And we use clustering algorithms to then take those, and we map existing bus routes on, and then we use clustering algorithms and different analytics-based approaches to create our own novel routes that help address that problem. And
Yeah, so here's a timeline of our production process. First, we want to brainstorm what are our minimum viable product solutions, and we came up with the planned transit app. And then we find out data sources. We did a lot of research on GeoJSON files, and that kind of took an hour and a half. And then the final couple steps were just building this presentation, prompt engineering the app, and then just writing a demo for you guys. So yeah, and then here's a demo.
all right. So for a demo, due to data availability reasons, we decided we were going to use the DC area. So here, let's go live. So this is a visualizer to help understand our proposed routes. So the analysis tool, basically it takes the AADT data that we have, it takes the congestion data, and it uses our existing bus routes to create now 5 new bus routes based on that. So you can see here it has like a route going this way towards Columbia Heights. I don't know much about Washington DC, but so it's suggesting that these 5 routes be added to the public transit system. We also, as a byproduct, create these different metrics. See, this is based on route number, which is something that route ID, which is something that is more informative if you actually know where the route IDs are. And then we have traffic categories. So it's high traffic volume areas, and then we have traffic distribution. So this is basically how it works. And in the future, we're planning to, create more tooling that allows people to plan when those buses run as well, and also, use it for different areas.
And one, I'll just add, we didn't mention it, but the use case for this, or the persona, is transportation planners, regional planners. It's not an end user type tool.
So it's like a B2B solution.
Exactly, yes.
Great, questions?
I think you mentioned you use clustering algorithm, but you didn't mention which one. Did you know that?
We used one of them. We used several. So one of them is a Louvain community detection So we use that to figure out, so we heavily prioritize like high population density areas. So we use community detection to declare these places like as important. The bus routes when they're being planned, it's like, hey, there's a lot of people that live here, they need buses. Or we do other things to prioritize different areas like grocery stores, schools, etc. Yeah.
Other questions?
What's the public data you use?
So we use data from data.gov. So actually, I think we have the link right here. We have, yeah, this is the bus route data. So this is the existing bus routes. And then we also have a,
Okay, got it.
yeah, so that's most of our like public data that we're using.
So the delay you're talking about, the total excessive delay, is that the delay in the bus route, or is that the delay in traffic?
It's in traffic.
As
It's in
the,
traffic,
okay, as the justification for the bus
Exactly,
routes,
yeah.
okay.
If there are no other questions,
If there are no other questions, this concludes our presentation.